I'm explaining the problem. You're using Sklearn's wardtree function for hierarchical clustering. I'll help you understand what the function's output, the linkage matrix, means. The linkage matrix is a two-dimensional array. N represents the number of merge operations done during clustering. It's always one less than the number of data points you started with. Think of it as a table with 4 columns and n rows. These 2 columns tell you which clusters were merged together in each step of the clustering process. Each row represents a merging event. This column holds the distance between the 2 clusters that were combined in the corresponding row. It shows how far apart those clusters were before they got merged. Yep, that's true. Each row describes a single merging event during the clustering. Absolutely. These columns point to the cluster numbers joined in that particular step. That's partially true, but needs clarification. The last column shows the size of the asterisk newly formed cluster, not the total number of points in the whole clustering. It's the combined size of the 2 clusters that just merged. I see that the linkage matrix is a 4-column array. The n means the number of merge steps taken during hierarchical clustering. It's always one less than the number of data points. Think of it like this. If you start with 10 data points, you'll need 9 merges to group them all into one big cluster. So, n is always n1. Each row describes a single merging event during clustering. Each row summarizes a step where 2 clusters, or data points, are combined. This column gives the index of the first cluster involved in that particular merge step. It helps me see what cluster is being combined with what other cluster. These indices could represent either original data points or clusters formed earlier in the process. This column mirrors column 0. It tells you the index of the asterisk second cluster combined in that merge step. It might be an original data point or an already formed cluster. It's the companion to column 0. This column contains the distance between the 2 clusters being merged. This distance is determined by the linkage criterion used in ward_tree. In this case, Ward's method. Think of it as measuring how similar or dissimilar the 2 clusters are. This column tells you how many data points are in the asterisk new cluster formed after the merge. It's the combined size of the 2 clusters you've just joined, not the overall size of all the clusters. I'm going to explain how Ward's method creates a linkage matrix for hierarchical clustering. It's a really useful tool for understanding how groups are formed during the process. The linkage matrix is a 2-dimensional array, always having 4 columns. The number of rows, n, equals 1 less than the number of data points you start with, because each row represents a merging step that reduces the number of clusters by 1. The final column tells you the size of the new cluster formed after merging the 2 clusters specified in columns 0 and 1. So, it's not the total size of all points but the combined size of asterisk only those 2 clusters after their merger. It represents the number of data points in the newly created cluster. The first 2 columns provide the indices of the clusters that were just merged to form a new, larger cluster. Think of them as the cluster IDs before they were combined. This column tells you the distance between the 2 clusters that were merged. This distance is calculated based on Ward's method, minimizing the variance within each cluster. I'm explaining how to interpret the linkage matrix from hierarchical clustering. It's like a step-by-step recipe of how the clusters combined. The linkage matrix is a table with 4 columns and n rows. N represents the number of times clusters were merged, and n is always 1 less than the number of data points you started with. Think of it like this. If you have 5 data points, you'll have 4 rows in your linkage matrix because you'll need to merge clusters 4 times to get one big cluster. This column tells you the index, the unique identifier, of the first cluster involved in a merge. This column tells you the index of the second cluster involved in the same merge. This column tells you how far apart the 2 clusters are before they're merged. This distance is calculated using the Ward method in Sklearn. This column shows the total number of data points now combined into this new, bigger cluster formed from the merge. It's not the total number of points in the whole dataset, only the points included in this particular step. I'll explain what a linkage matrix is in hierarchical clustering. Imagine you're grouping similar items. The linkage matrix keeps track of how these items are combined step by step, showing which items merged, how far apart they were, and how big the new group is. It's like a detailed record of the grouping process. The linkage matrix is a table. Each row describes one merging step. I will explain each column. This column tells you the index, a number identifying the position of the first group involved in a merge. This column contains the index of the second group being combined in that step. This column shows how dissimilar the two groups were before merging. A larger number means they were more different. This column shows the total number of data points in the new group created by the merge. I want to stress that each row in this table represents a single merging event in the hierarchical clustering. Think of it as a step-by-step recipe for how the groups got formed. It's really exciting to visualize the process, isn't it? This question tests your knowledge of the linkage matrix's structure and what each part means. It's all about understanding what the numbers in the table represent. This is TRUE. The first two columns clearly show which groups, identified by their indices, were combined in each step. This statement is FALSE. The last column shows the size of the asterisk new combined cluster, not the total number of points across all the merged groups. This phrase simply means the table of numbers that summarizes the results of a hierarchical clustering analysis. Think of it as a step-by-step record of how the algorithm grouped data points together. Each row in the linkage matrix shows one step where two groups of data points were combined into a single, larger group. Imagine it like building with Lego bricks. Each row represents taking two smaller constructions and snapping them together to form a bigger one. The first two columns of the table tell you which groups were joined during that merge step. These are represented by numerical indices. For example, if you see 3, 5 inches in a row, it means group 3 and group 5 were merged together at that step. Pretty straightforward. The final column indicates how many individual data points ended up in the newly formed cluster after the merge described in that row. It's the total count of data points in the combined group. It's the size of the combined group. Crucially, it's not the total number of data points in the dataset. This column tells you the index, a number representing its position, of the first cluster being merged in that particular step. Think of it like this. Imagine you're merging two groups of Lego bricks. This column tells you which pile of bricks, identified by its number, is the first one being combined. This column gives you the total number of data points in the newly formed cluster after the merge in that row. For example, if I'm combining two clusters with 5 points and 3 points, this column shows 8 for that merge operation. Similar to column 0, but this identifies the second cluster index involved in the merge. Continuing our Lego analogy, this is the number of the second pile of Legos being added to the first one. This represents the first merge operation in the hierarchical clustering. It would tell you which two initial clusters were joined first, the distance between those clusters, and the size of the resulting, larger cluster. This represents the last merge operation, where the second to last remaining clusters are joined resulting in the final, single cluster. This marks the end of the hierarchical clustering process.